What's up everyone? Today we're going to go over Leetcode 1035 Uncrossed lines. So I'm going to outline the video as follows. First we'll go over the input-output, then we'll look at the overview and DAG, and then we'll get into the code. So the input is going to be 2 integer arrays, and the output is going to be the maximum number of lines we can draw connecting from one array to the other without any crossed lines. So we have 1, 4, and 2, and we have 1, 2, and 4. The output in this case is going to be 2. So we can draw a line from 1 to 1, and we can draw a line from 2 to 2. Or we can do it from 1 to 1, and then draw from 4 to 4. Now let's go over some invalid cases. We can't have this scenario because 4 and 4 are the same numbers, but if we draw from 2 to 2, then there's a cross line, and that's not valid. In this case, we can draw from 1 to 1, but we can't reuse numbers. So we can't use this 4 connecting to this 4, and then reuse this 4 with the other 4 in the first array. So this is the valid uncrossed line case. I just told you that my goal is to maximize the number of uncrossed lines given these two arrays. Oftentimes, when we go for maximizing or minimizing or counting the number of ways, we go for dynamic programming. So how would I apply DP to this problem? Well, first I'm going to trust that a solution to this problem does exist, that I can find the maximum number of uncrossed lines, and that I can build it using some combination of subproblems. So what's a subproblem in DP? It's taking the original question, making it a little bit smaller, and asking the same question again. So what are some possibilities we have of making this problem smaller, such that we remain valid and we're not missing out on any potential lines? Let's see if we can remove one number. Okay, we took that 2 out. What if we remove a 4 from the bottom? Okay, are these valid? You might say, hey, we took out the 2 from here. Aren't we going to miss the line that goes from this 2 and this 2? Yes. Through this branch, we can't get that 2, 2 line, but that 2, 2 line is preserved over here, right? Similarly, you might say, hey, we took away this 4. We took it away. Aren't we going to miss this 4 and 4 line? Yes, but that 4, 4 line is preserved through this branch. So each of these are branches. What if we try taking away 2 numbers from the end? Can we take away 2 and 4? Let's think about it. Okay, well, I took them away, and I have a 2 and a 4, but there's no way that I can figure out how I can connect these lost numbers to these 2, because through this branch we don't have any more connections between the 2 and the 2 and the 4 and 4. Therefore, we would lose a connection, so we can't do that. But what if the problem was a little different? What if there was a 5 here? What if the problem looked like that? In that case, yes, we can take away the 2 numbers at the end of each array. We draw a line, and then essentially this problem is the same thing as the original. If you pay attention, you'll see that essentially 4 and 4 are at the ends of the 2 arrays, and that's how we connect our lines. We try to connect the lines from the end. So once we find this, then we can reuse that problem. Now let's look at the base cases. After we start taking away numbers, eventually we're going to run out of numbers. So that's where we run into our small or base cases. Let's look at a few examples, because these are the examples which actually return our values. So if we have 2 empty arrays, we have a return value of 0. If we have 2 arrays with only one number, and they're the same, we can draw one line. If we have two numbers, but they're different, then we can't draw any lines. Similarly, if either one of the arrays is empty, we can't draw any lines. In this case, we have two which are the same, so the B and the B are the same, so we can draw one line. So even among these small cases, we have prioritization. We have the most basic of cases, which is this one. So anytime it looks like we have an empty array, we're returning 0. Even this problem, which is technically a base case, as it's the smallest kind, where it's one and the same, after we draw one line, this problem boils down to this. This problem, since they're not the same, we can't draw a line, actually boils down to these two. Similarly, this problem, after we draw the line, boils down to this. So you can see how the smallest cases are actually reusing each other. And once you figure that out, you can actually use them to build the original problem back up and solve the question. So this is the DAG for this problem. We take away a number from either side, and then we say, hey, we can actually draw a line from either one of the branches. So 4 and 4, or we could do 2 and 2, and we get a +1, and we're left with this, and in this branch we're left with this. And we take away similar fashion from either end. When we run into a empty in either of the arrays, then we run into a dead end, and that would be 0. That returns 0. So essentially, this branch gives us 2, and this branch gives us 2. So the maximum number of uncrossed lines we can have for this problem is 2. Here's a more formalized version of the DP relationship. If I have 1, 4, and 2 as my array A, A1 to AM would be all three numbers, and A1 to AM-1 would be one less than the end, so it would just be 1 and 4. So what we're going to do if we're given this problem is first check if the last two numbers are the same, and we can draw a line, and then add 1 to the DP relationship of the M-1 and N-1. So we just ignore the last two, and we ask the same question again. If the n two numbers are not the same, then we try getting the maximum of either removing the top number at the end or the bottom number at the end. Now let's look at the code. So I wrote the code, and I used a map for memoization. First, we take the two integer arrays, get their length, and pass them into a recurrence function. So we take that as the pointers in the array. If either one of the pointers is 0, meaning we've gotten to the base cases, then we return 0. Then I create a key, which represents just the m-n, just a placeholder string. And if we contain it, then we return whatever values in the map already. Otherwise, we're going to calculate it. This represents checking the last numbers, the n numbers, and seeing if they're the same. If they are, we're going to recursively call and add 1 and store it in our map before returning it. Otherwise, we're going to recursively check left and right branches by removing a number from either the top or bottom array. And whichever one is larger, we put that as our max, store it, and return it. Now let's look at the DP tabular version. Here's the tabular DP code. We take the two arrays, grab their lengths, and initialize a new 2D array of integers. The values in the DP 2D array represent the maximum number of lines we can draw. So if I was comparing 1 and 2 and 1, 4, and 2, the maximum number of lines we can draw is 2. Using this, we find our final answer of comparing the two original arrays. So this is going to be the base case, and this is going to be the case where the numbers match, and these are the branching cases. Now let's look at the space and time complexity for the memoized and tabular approach. The space and time complexity are going to be different for each approach. For memoization, the space complexity could be O of m times n based on the size of the map. The time complexity in the worst case could also be really large. It could be 2 power maximum of either m or n. Even though we're trying to prune and eliminate the cases that we're already seeing, we could have a bunch of cache misses and essentially boil down to the naive recursion. So if we're doing a tabular approach, the space and time complexity are going to both be O of m times n. This is because we're using a double for loop and there's no recursion happening. So that's how you solve Leetcode 1035. Let me know what you think in the comments below, and if you want to see more, don't forget to subscribe.